In the deep, cold shadows of Saturn's orbit drifts a small, unassuming moon. From a distance, it looks like a snowball, a featureless chunk of ice, spinning in silence. Its name is Enceladus, just one moon among dozens. Tiny, frozen, ignored for most of human history. But sometimes, the quietest places hold the loudest secrets. And in 2005, Enceladus revealed one of the greatest surprises in the history of space exploration. From its southern pole, something unexpected burst into the void, a plume of vapor, towering into space, rich with water, organic compounds, and mystery. It wasn't just beautiful, it was impossible to ignore, because that eruption suggested something extraordinary. That beneath Enceladus' frozen crust, there was heat, and water, and chemistry, that somewhere inside this icy moon, there might be conditions for life. This is the story of Enceladus plumes, the spacecraft that found them, the ocean that feeds them, and the clues they carry about life, about the solar system, and about us. Enceladus was discovered in 1789 by astronomer William Herschel. It was named after a giant from Greek mythology, a name far grander than the icy rock it described. For over 2 centuries, it was largely ignored. Too small to be interesting, too distant to investigate. When Voyager flew by in the 1980s, it caught blurry glimpses, a moon covered in bright ice, oddly smooth in some places, fractured in others. It reflected almost 100% of the sunlight that hit it, brighter than fresh snow, but it showed no signs of life. No clouds, no atmosphere, no activity. It was just one moon among many, until the Cassini spacecraft arrived. Cassini wasn't built to search for life. Its mission was to study Saturn, its rings, and its moons. But in 2005, it flew past Enceladus. And what it saw changed everything. As Cassini passed over the southern hemisphere, its instruments lit up. There was heat, faint but undeniable. And then came the shock. Something was escaping into space. Water, not just vapor, but ice particles, erupting hundreds of kilometers above the surface. Cryovolcanoes, geysers shooting material from deep beneath the moon. Cassini had discovered plumes, jets of water erupting from narrow fractures near the South Pole. These fissures were nicknamed the tiger stripes, long, warm cracks that vented vapor in rhythmic bursts. At first, scientists were stunned, then skeptical. Could such a small moon really sustain active geology? The answer, over time, became clear. Not only was Enceladus geologically active, it was world-shatteringly so. The plumes weren't a one-time event. They were constant, fed by something vast and hidden. The plumes had a source, something big, something deep. Cassini began flying through the eruptions, literally passing through the vapor as it burst from the surface. And what it found was astonishing. The plumes were made of more than just water. They contained salts, like sodium chloride, the kind we find in oceans on Earth. They contained ammonia, methane, and complex organic molecules, the very building blocks of life. And most critically, they contain molecular hydrogen, H2. That hydrogen is a byproduct of chemical reactions between water and rock, reactions that, on Earth, fuel microbial life near hydrothermal vents at the ocean floor. In other words, Enceladus didn't just have liquid water beneath its surface. It had a saltwater ocean, an ocean that was chemically active, in contact with rock, and capable of generating energy. This wasn't speculation. It was data, and it redefined Enceladus forever. Every new pass revealed something new. Cassini's instruments detected tiny silica particles formed in environments over 90 degrees Celsius, consistent with hydrothermal vents at the ocean floor. it wasn't just water and salts. There were complex organics, molecules containing carbon, hydrogen, oxygen, and nitrogen, the fundamental ingredients of amino acids and life as we know it. Even without landing, scientists could read the chemistry of Enceladus Ocean, sampled through space. It was like flying through the spray of a whale and discovering its diet, its ecosystem, its biology. Cassini couldn't tell us if life existed beneath the ice, but it showed that all the ingredients were there: water, heat, organic chemistry, and a mechanism to deliver samples directly into space. It was one of the most profound discoveries in planetary science, because Enceladus was no longer a frozen ball. It was a living ocean world. Cassini's mission ended in 2017. After 13 years orbiting Saturn, the spacecraft was deliberately plunged into the planet's atmosphere to avoid contaminating Enceladus or Titan with microbes from Earth. But before its fiery end, Cassini gave us one last gift. Its final flybys of Enceladus were timed to pass through the densest parts of the plumes, gathering high-resolution data on their structure and contents. It confirmed that the ocean beneath Enceladus was not isolated, but active, stirred, vented, constantly interacting with the icy shell above. It proved that the internal heat of the moon, generated by tidal forces from Saturn's gravity, was enough to keep water in liquid form, even this far from the sun. Cassini had shown us that habitability doesn't require Earth-like conditions. You don't need sunlight or a thick atmosphere. You just need energy, liquid, and chemistry. And Enceladus had all three. Could there be life in Enceladus Ocean? The idea is no longer science fiction. It's a scientific question. On Earth, life exists in the most extreme places, in the boiling waters of hydrothermal vents, in subglacial lakes beneath Antarctica, in the dark, pressurized abyss of the deep ocean. These environments are cold, dark, and hostile, but they teem with microbial life. If life can thrive here, cut off from sunlight for millions of years, then perhaps it can survive on Enceladus, too. It wouldn't look like us. It wouldn't build tools or cities. But it might exist in microscopic colonies, feeding on hydrogen and minerals beneath the ice. And here's what makes Enceladus so extraordinary. We don't need to dig, or drill, or melt through kilometers of ice. The ocean is venting itself into space. The samples are waiting for us. All we have to do is catch them. NASA knows the stakes. That's why new missions are now on the table, designed not just to fly by Enceladus, but to search for biosignatures directly. One proposal, the Enceladus Orbolander, would orbit the moon for 18 months, flying through the plumes and analyzing their contents in exquisite detail. Then, it would land near the tiger stripes and search for complex organic molecules, proteins, lipids, or even cellular structures. Another idea, ELF, the Enceladus Life Finder, would be smaller and faster. A dedicated flyby mission with ultra-sensitive mass spectrometers, tuned specifically for biological signals. Meanwhile, private companies and international space agencies are proposing their own concepts. The excitement is growing. The technology is catching up. The window is open. Because the data from Cassini still haunts us, it begs for follow-up. And every day, those plumes continue to erupt, offering the universe's most accessible alien ocean sample. The only question is, will we go back? Enceladus is not large. It has no cities, no lights, no sounds, but it has spoken in the language of chemistry, in the rhythm of eruptions, in the silence of space. It tells us that even in the coldest parts of the solar system, life might emerge, that oceans can hide in the most unlikely places, that worlds once ignored might be more alive than we imagined. It challenges our assumptions. That Earth is special, that life is rare, that intelligence is the measure of meaning.